Testing on YouTube. Testing on YouTube. I gotta fix this link here. There we go. All right, link is fixed. Seems like it's working on YouTube. And then we just gotta wait for X, and we're almost there. Question from the chat: what is the state of the art in RL? So state of the art usually refers to a specific benchmark. Reinforcement learning is a very broad, general approach. So it's kind of hard to say what is the state of the art in RL because it's task dependent. But if I had to say something, I would probably say AlphaZero, something like that. You know, I feel like AlphaZero is state of the art in RL in terms of that's probably the most impressive demo of reinforcement learning I've ever seen. Maybe, you know, RLHF, even though that's actually a relatively simple RL algorithm. But if by state of the art you mean the most impressive, then that's what I would say, AlphaZero or the utilization of RLHF for instruction tuning. But the real definition of state of the art requires a specific benchmark. Hope that answers your question, 2ARX. All right, I think we're live on X as well. All right, let me spit out this gum, take a sip of coffee, and let's get this started. Got some espresso here today. I've been taking a break on the yerba mate. It's just too high caffeine. Maybe I needed it. All right. Welcome, everybody, to another HooPost stream. Today, we're going to be looking at a bunch of different AI agent papers that came out in the last couple weeks. Stuff is starting to heat up here, and I think we're starting to get to the point where it's kind of, we've gotten to AGI. You know, I keep saying this time and time again that under my definition of AGI, large language models already are AGI, so I kind of more make the distinction of, okay, we already have AGI. What most people are kind of talking about is the idea of ASI, artificial superintelligence, as opposed to artificial general intelligence. But yeah, these papers today, I think if you're not convinced that we're already kind of operating under this kind of AGI paradigm, I feel like these papers should convince you of that. How's it going, Majetti? And yeah, so if you want to find any of the papers or any of the links that I go to in this talk, feel free to go on GitHub, and I have a repo called Docs, and you can find all the links and all the archive papers that I will be looking at. So we're going to start with this paper right here. This is a paper that was released on the 15th of February 2024 called OS Copilot. This is operating system, which is basically something like Windows, Apple, Linux, right? It's like the software that allows you as the user to interact with the computer. So towards generalist computer agents with self-improvement. This is coming out of a couple different Chinese institutions here, University of Hong Kong, East China Normal University, and Shanghai AI Laboratory. And in this paper, they basically get a vision language model paired with a large language model. I think the specific one that they use is GPT-4 Turbo and GPT-4 Vision, I think, as well. But basically, they're going to operate a Mac OS computer using a large language model. And it can do all kinds of things, right? So here, for example, in this very first figure, usually on a paper, the first figure is supposed to be kind of the most impressive figure. They're picking out of all the different pictures they could have shown you, they picked the most impressive one to show first. And here you go. It is calculating and drawing a chart in Excel, creating a website, So it adjusts the work layout and theme. It plays music, calculates and fills a spreadsheet, draws a bar chart, generates files, and builds it to a web page. So it basically builds a web page, I don't want to say from scratch, but it builds a web page which requires going into multiple different programs inside a Mac OS computer. Autonomous interaction with the computer. And you're seeing some people start calling this theme of agents called the autonomous or the self-operating computer. So basically the idea of a computer that operates itself. And they're calling it Friday, which is kind of a weird name for this one, but it's a self-improving embodied agent for automating general computer tasks. I don't quite agree with the use of the word embodied here. Embodied generally refers to whenever you're putting an agent inside an actual body, like a robot. And it's okay if you use the word embodied for a simulated agent that is inside a simulated body inside a simulation of a 3D world, but embodied kind of seems like not the right word for something that lives inside this like 2D UI and like clicks around on things. But in tandem with this paper, so if this paper is basically doing things in the Mac OS, there's another paper that was released just a week earlier, 8th February 2024, and this paper is from Microsoft itself. So here you have a bunch of different people working at Microsoft, and this one's called UFO, a UI-focused agent for Windows OS interaction. So now we have two different papers. We have an agent paper for Mac OS, and then we have an agent paper for Windows OS. And this one, they kind of bury the lead, but it's also GPT-4V and GPT-4 in tandem as well. I think I have it highlighted somewhere here, but I lost it. Yeah, GPT-4 Vision and GPT-4. So is that not evidence of GPT-4 being AGI? You know, if it can literally operate a Mac computer and a Windows computer with just a little bit of prompt engineering and a little bit of kind of massaging it into this little loop that is reminiscent of a sense plan act loop. I feel like that to me kind of proves the point, right? So here you have their figure one, very similar to the figure one here, except in this one, this is going to involve a Windows computer. So you see it's doing a bunch of different things. It's extracting information from a Word document. It's scrolling through the Photos app in order to find specific figures. It then creates a PowerPoint and then sends that PowerPoint via an email. So that's 4 different applications on a Windows OS that it needs to do to accomplish a task. So let's look at the abstract for this one. Applications on Windows OS, it's using GPT Vision. It operates within individual applications but can also span multiple applications, and as a user, the only thing you're providing is just a very high-level natural language command, such as, hey, I want you to create a PowerPoint and send it to my friends, right? And then it does all of the rest itself. So we've seen an evolution of these large language models into large action models. This terminology feels a little bit cringe to me, you know, because nothing's really changed, right? Both of these papers, what they're really doing is they're just taking an existing large language model, which would be your GPT-4, and a VLM or vision language model, which would be your GPT-4 Vision, and then combining them with a bunch of different prompt engineering tricks, some chain of thought, just tricks that people have been coming up with, putting them inside kind of a general framework, and then calling that a large action model. I don't know about that. You know, it's still the same LLM as it was before. But anyways, we're kind of rapidly approaching this world in which we're going to have general intelligent agents that can comprehend user requests in natural language and autonomously interact with the UIs and applications built on Windows and Mac OS and Linux. And even just a couple weeks ago, we were looking at some agent papers where they did this on smartphones. So that's how fast the research field moves. Just a couple weeks ago, most existing agents predominantly focused on smartphones, and they were interacting via an API. So even though these agents, right, they can interact and do things on a cell phone, they're doing it all via API. So these are still using API, which means they require an internet connection. They're not doing any of the inference on the device itself, but you could see how a PC that's running Windows, it's powerful enough to run a VLM locally and an LLM locally. So a self-operating computer is probably going to be achieved for a PC before it's achieved for a smartphone. I think you'll see this achieved on a PC, and then people will distill it into something that can run on a cell phone. But pretty crazy stuff. So UFO stands for UI Focused Agent. Obviously, UFO is a pun on unidentified flying object, which have now been renamed into unidentified aerial phenomena. UAP is like the new word for UFO, but it basically just means like an alien spaceship. How's it going, Khalil? How's it going, Skeletal Ghost and Adam? They're going to take our gerbs. Yeah, they're not just going to take our jobs. They're going to take everything, you know? But take is maybe not the right word. I think they're going to do these things for you, but you're still going to be able to do all the things you want, right? So hopefully the value add and the gains that we get from AGI and ASI get distributed enough that everybody gets to enjoy kind of a utopian life. But it could be the case that all the accumulated gains and value of having AGI and ASI kind of bubble and trickle up to the top 1% of the people who already have all the money anyways, and that's going to be a pretty ugly situation. But I think we'll figure out the social stuff, and we'll figure out how to kind of make everybody win now that we've discovered AGI, and nobody really needs to do anything anymore, right? Because these LLMs can largely do anything. How's it going, Ed? Okay, so here they talk about other attempts where people have kind of done these multi-prompting type systems, such as MetaGPT, where you had distinct roles assigned to individual GPTs. And in this paper, they're going to be coordinating multiple specialized agents to form an AI team tailored for complex tasks. So what do these things look like? So let's actually scroll down to the kind of figure 2 for both of these papers, which is an overall architecture of UFO and then an overview of the OS Copilot framework. So there's a little bit of difference here, but there's also a lot of similarity. And I think that's the important thing to realize here, is that there's kind of repeating motifs that you see here, such as memory, right? So there's this concept of memory where the agent that is controlling your OS is storing previous states, it's storing previous actions, it's storing the user request, it's storing images of previous screenshots. And you see the same thing here, right? Here they're kind of breaking it up into either procedural memory or declarative memory, where declarative memory is stuff that kind of stays a little bit more static, such as the user profile, which is information about the user, and then semantic knowledge, which is kind of more generic, high-level knowledge about this specific situation. But then procedural memory is kind of more your tools or your functions, as they're called. Sometimes the API is used, even though that's kind of a broad term. But this is actions is another kind of word for this, the action space, right? The things that the LLM can actually do, or the agent can actually do. So here you have the same kind of idea here. You have this idea of actions and then memory. Okay. Given a subtask, the configurator maintains a working memory that is responsible for retrieving tools, knowledge, and any other relevant information. So you have this kind of retrieval augmented generation idea, right, where you have kind of cold storage, cold memory, where you're storing all this information, and then your LLM that is actually outputting either thoughts or feedback or criticism or specifically actions that it wants to take. It's going to be loading things in and out of its context. But even this is something that I feel like is probably going to maybe go away a little bit, right? Even yesterday we were reading the Gemini 1.5 paper, and in the Gemini 1.5 paper, they've basically 10x'd the context of a transformer-based language model. So it's not even just a language model, it's a multimodal model. So in Gemini, it's consuming like 3 hours of video and over 10 million tokens, right? So I feel like this entire all these different design patterns that people are coming up with where they're creating this kind of these memories, right? Procedural memory, declarative memory, or here they're calling it actions, previous observations. Like, I think that stuff is going to kind of go away because you're not going to need to do this kind of retrieval memory kind of abstraction whenever you can just fit everything inside the context. So I think, if anything, these systems are actually going to look more complicated than the AGI that will be controlling your computer at the end of this year, right? I feel like the way that this is progressing, probably by the end of this year, you'll have something that can control your computer, and you're just kind of talking to your computer in natural language at a very high level, and then it's kind of doing everything for you. And companies will have hundreds of these things kind of just running constantly. We already kind of heard some news that at Meta, right, Facebook, they have basically bots that are just generating unit tests and then just running more unit and then just designing unit tests, pushing their own PRs to create more unit tests. So as an individual, you'll likely have this type of software running on your computers, and it'll just do your daily tasks. But companies will have lots and lots of these things running. Just, I don't exactly know whether, I wonder if this will be captured by the OS provider or whether this will be something that gets done by a third party, right? The fact that Microsoft has people, or obviously they have a team that's working on this, I could see this being deployed as a product on Windows. I don't know what we're at. Are we at like Windows 12? I think would be the next one. So maybe Windows 12 comes with like a built-in agent that basically does this for you. But maybe not Apple, right? It feels like Apple maybe is stuck a little bit behind because this is not even a team at Apple, right? This is just some other random academic group that created the Apple version of this for Mac OS. So I don't know. Maybe we end up in a world where there's multiple companies that offer you software to remotely operate your computer, or maybe kind of it becomes more of a walled garden and the person who's making the OS, or the company that makes the OS, is the one that sells you this product. I don't know, still to be determined. But let's learn a little bit more about this. So our proposed UFO stands out as a multimodal LLM agent framework. So it's multimodal because it's consuming observations and text. So it's not just the user request, which is text, but it's also visual tokens, in this case, just literally screenshots of your screen. It chooses an application to fulfill user requests. It iteratively executes actions on the selected applications until the task is successfully concluded. It leverages the multimodal capabilities of GPT Vision and then uses control interaction module to ground their actions. So what does grounding of actions mean? So you might have seen this pop up in other vision language model papers, but action grounding is this idea that by annotating and providing basically these little boxes here, right, you help the vision language model. And it's a weird thing to think about, but basically we've gotten to let me see if I can exactly get the definition here, but I think they define it here. I thought they defined it here. Yeah, here you go. So the way that they ground these actions is they take a screenshot and then they highlight with a red rectangle the actions that are basically buttons, things that you can click on, like menus that you can click on, and then they put a little number on each of these. And this facilitates a better understanding of the function and location of UI elements. So it's kind of a weird situation, right? Where your vision language model, in order to improve the performance of it, you basically give it little numbers on the screenshot so that rather than saying, hey, what is the XY position of the mouse that I need to put in order to click on the increase the size of the font button, you can say, okay, well, which button do I need to click? And it'll be like button 100. And then that makes it easier for the VLM to kind of reason about all the different actions that it has access to. And on that vein, here's another kind of piece of evidence to show that that's actually kind of the way that this is going. This is a paper called Pivot, Iterative visual prompting elicits actionable knowledge for VLMs. This is released 12th February 2024, so also very recently. This is coming from Google DeepMind. But even though this is a DeepMind paper, right, they keep using VLM, and I'm like, okay, why don't they tell me what the VLM is? And then they do finally tell you what the VLM is, and it's kind of a weird situation. They use GPT-4V. So you have a Google DeepMind team using GPT-4V to show that you can basically zero-shot tasks from a vision language model. And they use this same kind of like grounding trick, right, where they basically take an image, they feed that image into the VLM, but before they feed it into the VLM, they draw these little arrows on it. Like they literally draw arrows into the picture and then ask the VLM which of these arrows makes more sense given the current situation. Let me close this. Which is weird, right? Like, why does that work? That's the most human thing ever, right? So, like, if you were sending a screenshot to a human, you might annotate that screenshot and, like, circle with a little red edit, you know, like, hey, what is going on here? Or, like, hey, what do you think about this button? Or, hey, which of these two buttons should I click on? And that same trick works with vision language models, which is the most anthropomorphic thing I've ever seen, and just further adds more evidence to this claim that I made at the beginning of this stream that we're basically dealing with AGI here, right? So here you go. Here's step 1, step 2, step 3, step 4. So this is a robot that's kind of navigating, and it's trying to solve this task here. Help me find a place to sit and write. And then it basically just adds a bunch of random arrows, and then it says, choose out of these 14 arrows. It picks those 3, and then from those 3, it basically does some action, right? So in this case, the action is movement, and the arrow represents the direction of movement, but they also do it with some kind of robot manipulator here. So here you have an arm. This is the RTX arm, the little one-armed robots, general purpose robots that Google has. Same situation. They're kind of just adding these random arrows, and then the VLM picks from that. So this idea of grounding, where you basically annotate a UI or a real image with these red bounding boxes or red arrows or numbers, and then that drastically increases the performance of the vision language model on that task. Kind of a crazy idea, but that's something that I see popping up time and time again. What are the chances question from Nisio, what are the chances we see this running on device? Seems pretty compute intensive. Probably pretty high. I think that I've run vision language models on my computers locally, right? So I don't know if I have instructions on how to do that, but it's pretty easy. You can just run, like, it's easy to do on a Docker or on a Linux computer because you can just have a Docker container running it. I think with Windows, it might be a little bit harder running this type of thing on Windows. You're going to have to download the whole WSL2 crap, and Docker is a little bit more annoying to work on Windows. I don't even know if you can get Docker to access the GPU on Windows yet. I think that might still be kind of like a beta feature, to be honest. But I don't think they're necessarily going to want that. I think the way that the Windows self-operating computer or Windows agent is going to work is that Windows has GPT, right? They're the same company effectively. So I think it's very unlikely that Windows runs the AI locally on your computer, right? Because Windows wants to know what you're doing, right? So they have a benefit by you sending the requests via API. They're going to get all that information, right? They're going to know everything that you're asking. They're going to see screenshots of your computer. They're going to have all the pieces of information in your computer. They're going to have that, and they want that, right? They want that information because they can use it to better sell you stuff. They can use it to create better products and so on. So I think that locally run AI agents that operate your computer probably won't happen for Windows computer because Windows will just use GPT via API. But for something like Apple, maybe they do allow you to do that, right? Apple's a little bit more privacy focused. It could be a situation where Apple's also, I think, easier to deal with the Docker containers. And I think the Apple chip is a little bit better. So you could probably distill a vision language model from something like GPT-4 Vision or GPT-5 Vision once it comes out, and then have it run locally. So I don't know. I think we'll have both. Ollama now supported on Windows. There you go. I don't know of any vision language model on Windows, though. Okay. Ground their actions. Constructs a local plan for future steps. Here's an illustration of the ACT agent. So this is everything that it's receiving, and this is everything that it outputs. So you can see it's receiving a previous screenshot and the annotated screenshot. So here's the annotations are those little bounding boxes with numbers on it. And these are images, right? So basically the way that this system or framework consumes this is it'll feed those images into GPT-4 Vision. GPT-4 Vision will give it text tokens, and then those text tokens are combined with the memory, the examples, and the user request, which are all also text tokens, and then all of these text tokens together get fed into the ACT agent, which is an LLM. So even though the ACT agent is multimodal, the multimodality is only when you look at it as a giant system, right? The actual agent that's actually doing most of the planning and the decision making is a pure language model. And I think that's another thing that's going to go away. Like, even for my projects, when I was working on some robotic stuff, I had this same distinction, right? Where I'm using the vision language model just to basically summarize what's in the text or in the image. And then I'm using the language model to do all the kind of planning and actually heavy lifting. But I think you'll see this distinction disappear. Eventually, the vision language models are going to get cheap enough in terms of compute memory and inference cost that you won't need this extra LLM in the loop, right? It'll just be one vision language model that consumes all of this, right? And even at that point, we won't even necessarily call it a vision language model, right? Like Gemini 1.5 consumes text tokens. It can consume image tokens, it can consume audio tokens. So technically, Gemini 1.5 is a VLM, right? But we don't really call it a VLM because it's kind of like almost grown beyond that. It's almost like a multimodal language model, MLLM. I guess the output is only text, so maybe that's how we make the definition. A VLM consumes images and text and outputs texts. LLM consumes text, output texts. MLLM consumes any type of modality and outputs text, but we have yet to see something that consumes multiple modalities and outputs multiple modalities, but entirely within the same model, right? That does exist, but only when you like kind of have multiple models acting inside the umbrella of one larger system. Okay, so just to give an example of like kind of what these things look like, this is what it actually looks like inside the UFO model. So as the user, you say, help me quickly remove all the notes in the slide. And the UFO model says, okay, here's my plan. And you can see it's talking. This is the chain of thought. So chain of thought is basically a chain of thoughts. So basically you can see here how it's created this little plan. So this is all just the LLM outputting. Here's all the different things I could do. I could click this button. I could click this button. I could open this button. And then it says, okay, here's the observation. So this is what's coming out of the vision language model. So the vision language model is seeing the screenshot. And then it's saying, okay, here's the description of the screenshot. Then you have the LLM saying, okay, well, given that description of the screenshot, here's some more text tokens. And then we're going to select this particular control. So there's this notion of kind of an action space, right? And maybe that's where the word large action model might come in. So if we just said that a large language model is a model that outputs text tokens, then maybe a large action model is a model that outputs action tokens. And what the fuck is action tokens? Action tokens is basically tokens that represent some action. So they're kind of like hard-coded. And I think there's an example here in this paper about what action tokens might kind of be like. So, for example, this is a interactive agent foundation model paper coming out from a huge group of people from Stanford University, Microsoft Research, UCLA, blah, blah, blah. Also around this same timeline. But in this one, they also have this idea of this like agent system, but Specifically, what I want to talk about here is this idea of action tokens. So action tokens correspond to the actions used, blah, blah, blah. All tasks include a token to indicate starting actions, blah, blah, blah. For Minecraft, there are an additional 23 button actions. We discretize the mouse actions to 100 bins along the X and 100 bins along the Y. 11 button actions, this is some kind of video game, 2 joysticks, 256 possible values for rotation, and 4 values for magnitude, resulting in a total of 520 joystick action tokens. So whenever you have a autoregressive transformer model, which is outputting a sequence, right? What it's doing is it's basically creating, it's kind of, you can think of it like it's doing classification at every step, right? So every time it outputs one token, what it's really doing is it's picking that token from a vocabulary of possible tokens. So usually for text, that's something like 30,000. So basically there's 30,000 possible tokens that it could have chosen. And what it's doing is it's picking the one that it thinks is the most likely, right? So for text, you might have 30,000 possible tokens. For vision language model, you're going to have visual tokens, and those have usually some discrete amount of tokens. Usually they're discretized. But you're going to do the same thing, right? So you're going to have this sense of action tokens where for every single type of task, you're going to say, okay, well, here's all the possible tokens that you could output as an action at this particular point. And this is this idea of action tokens. But the problem with this is that you have to define this. So this gives me a little bit of PTSD over the way that reinforcement learning was done 5-10 years ago, right? Where deep reinforcement learning 5-10 years ago, whenever you see deep reinforcement learning doing all those Atari games and stuff like that, they call it end-to-end because a lot of times it's consuming the image, the raw image from the Atari game, and it's outputting the action. And the way that it outputs the action, right, that action space is basically predefined. So before you even train this reinforcement learning agent, you're already saying, okay, here are the 4 possible buttons that it can output at this particular time. And the problem with that is that no 2 tasks are going to have the same buttons, right? So a robot operating in the real world is going to have a completely different set of buttons or a completely different action space than a robot that is navigating, or it's going to have a completely different action space than a AI that's playing Bleeding Edge, or it's going to have a completely different action space than an agent that operates like this on your OS. So I feel like this action space idea is like a vestigial component left over from the deep reinforcement learning era where people were doing this end-to-end stuff. And I feel like eventually the action space is going to be pure text. And this isn't entirely a new idea, right? If you look at the Voyager paper, which is a paper where they basically make an agent for Minecraft, the action space of that is text, right? Where basically the agent creates functions, it writes a function in text using some kind of Minecraft API, and then runs that. So the agent isn't limited to a specific action space that has to be defined per task. Basically, if the action space can be formulated in text, then you never have to change that agent because that action space of text is always compatible with any task. So I think that's probably what we'll see in the future is agents that the action space is text, which means they don't have to be predefined for some specific task or application. Okay. LMM is my preferred acronym, Large Multimodal Models. I think I like that one too, Majetti. Okay, so the way that they do this in Windows is they use PyWinAuto, which I guess is like a way to control Windows using Python. So it gives you the ability to do things like click, set text, summarize, get text, scroll. So as soon as I saw this, I was thinking, I wonder what video games you can control entirely with this, right? Scroll bar, hyperlink, combo box. Interactive mode. UFO offers the capability to engage in interactive and iterative interactions. Users have the flexibility to request UFO to enhance the previous task, propose an entirely new task, or perform operations to assist UFO in tasks, right? So what they're basically saying is that it's not like you have a user request and then you go make yourself a coffee for 20 minutes. At any point in this kind of loop that it's running over and over again, you could kind of interrupt it and say, hey, I actually want you to do something else. And because the language model is basically AGI, it can figure that out, right? It could kind of roll with the punches and be like, okay, well, actually, I was going to do this, but you just changed my mind. You told me to do this, so now I'm going to do that. Okay. Is there other stuff in this paper? Yeah, this is something that had me thinking. So one thing that they complain about here is that annotating all these controls can clutter the application UI screenshots. Notably, some of these controls may prove unlikely to be useful or relevant for fulfilling user requests. So one of the things they noticed when they were doing this research is that for a lot of UI-based applications on Windows, there's a lot of buttons, right? So here, for example, this is PowerPoint. There's over 100 buttons here, right? And the larger your action space is, the more difficult it becomes, right? So in the original reinforcement learning Atari games, there's only like 4 buttons on the Atari controller, right? I think there's like the 4 directions, and then there's the A button and then the B button or something like that, right? So that's a very small action space. And here, because there's so many different things you can click on, the action space is so big that it's actually makes the problem harder. And to address this, one thing that they do is they basically filter it. So they say, okay, here's 100 different buttons that I see on this screen. And then they ask the UFO LLM itself to basically say, okay, filter this. So here's the list of 100 buttons. In such scenario, UFO intelligently returns a refined list of control candidates of interest. So it says, okay, here's 100 buttons. Filter this down to 10 buttons for me. But I feel like this is also... The reason I want to talk about this is because I feel like the way that we're moving, we're going to see drastic changes in the user interface and the user experience, right? So all these different applications, whether it's Word or PowerPoint or email or all the different Excel spreadsheets, different things that you have in the Mac OS, all of those were designed over the past couple decades based on human feedback, right? So all of these applications were designed such that they're easy for a human to use. But I think as we see more and more of these applications only being used by AIs, we're going to see the UIs drastically change, right? So what does a UI for PowerPoint look like whenever 99% of PowerPoints are created by a language model, right? What does the UI for a video game look like when you're no longer sitting there with a controller moving? You're literally just talking to the computer and it's playing the video game for you. So I think we're going to see an interesting transition over the next couple years as all these applications basically, rather than optimizing with respect to kind of human usability, they optimize with respect to agent usability, right? And you could say, hey, that doesn't make any sense. Like the people at Windows, they're still going to want to have it focused on humans, but there's a monetary incentive here as well, right? Because think about this. If there's 100 possible buttons here, that means that every time they do a screenshot, they have to run this entire language model again to do this filtering process, and then they're paying for that, right? So you're only paying for GPT via subscription. So if you're happy with the product that you're getting, regardless of whether it's doing 10 inferences or 1,000 inferences, Microsoft is heavily motivated to make it the least amount of inferences as possible, right? So Microsoft is going to want to reduce the total amount of inferences it takes to autonomously operate your computer, right? It's not going to be profitable for them if they have to perform 1,000 GPT-4 inferences for you to open up PowerPoint and click on the font button and change it to a bigger font, right? They ideally want to reduce the total amount of kind of individual tokens that are being predicted by this framework. So I think that will become kind of one of the driving metrics is inside Microsoft, inside Apple, right? You can envision these situations where a PM is like presenting to a VP and they're like, oh, look at this. We redesigned the PowerPoint UI, and now our agents can perform tasks in 5 actions as opposed to 100 actions, which leads us to a 100% savings on our inference cost, right? So I feel like it's just a matter of time before these windows become almost unusable for a human, right? So you as a human, like you'll be like, I don't even know how to click on things. And maybe that's a joke that people will do, right? Maybe the generations below us, right? The same way that we make fun of boomers for like chicken typing on a keyboard, right? And we're like, wow, look at this boomer. They're chicken typing on a keyboard. They don't even know how to type on a keyboard. Maybe the generations under us will make fun of us because we're like sitting around like trying to click on things with a mouse, and they're like, what are you doing? Why are you clicking on things? Just tell the agent to do it for you, right? So I don't know. I get excited about thinking about the future and how things will change. And I feel like this is something that seems like an obvious change in the kind of driving forces that will result in a different kind of local minimum that we will end up in. Here's a little section here on safeguarding. UFO intelligently assesses the sensitivity of each action, significantly safer and trustworthy agent. So basically, anytime it's clicking on anything, it'll basically determine whether or not it's even possible. So this is not a good thing, right? So if I said that this part is generally good because it'll make the UIs, or maybe it's not even good. If this makes the UIs harder to use as a human, easier to use for an agent, this is kind of the creepy part, is that, okay, well, now you're doing things on your Windows computer, but there's a screenshot of your Windows computer getting sent every single second to the Microsoft data centers. And every single second, there's a safety model that is looking at that screenshot and saying, is this safe? Am I doing the right thing? So anybody who does anything with a Windows computer that is at all sketchy, right, whether that's porn or writing ransom notes or whatever weird shit you guys are doing, that's going to kind of go away, right? If these computers are being controlled via an agent, and over the years they become almost impossible to control as a human, right? You have to interact with them via this agent. You're not going to be able to do anything on a computer that basically isn't implicitly applied or explicitly approved by Microsoft. So we're very quickly going to get to a situation that's very similar to that Odyssey 2001 movie, where the guy is sitting there and he's like, open the bay doors, and the computer's like, I'm sorry, I can't do that. I can't open the bay doors, right? So you can imagine in a couple years, you'll be sitting there and you're like, hey, I want to pull a prank on my friend. Can you buy? And the computer's like, I'm sorry, I'm not going to let you do that. You shouldn't be pulling pranks on your friends. So kind of a little sketchy there, that we're going to lose the ability to use our computer to do things. Okay, so that's these two papers here, right? And I wanted to kind of show that these agents are not just limited to operating computers. We're seeing them kind of pop up everywhere. So obviously I showed you guys this one here. This is what they call the foundation model agent. So this is just an agent that, again, has the same, it's not really a single model. It's the same idea, right, where you have basically a sense, plan, action loop, and the sense, plan, action loop has this same concept of memory and some kind of set of functions or tools that it's calling, right? It has this notion of an action space, which is some limited vocabulary of action tokens that it can output. But here they're trying to make it a little bit more high level or generic, right? They use the word foundation model. So they want to basically train a single agent that operates on a variety of different embodiments, in this case, different tasks, right? Such as robotics, manipulation, navigation, gaming, VR, AR, mixed reality gaming, and then healthcare, diagnostic. This one's a little bit creepy. This is basically, they have the agent looking at images of like a healthcare situation and then telling you what's happening. Let me see if I can pull that example up because it's a little weird. Yeah, so here, video captioning, start frame. And here you have like a picture of a guy in a bed. And then it says, the patient is awake and calm. The patient is cooperative. The patient is alert. And the same foundation model is basically also doing things like this, right? It's operating this robot that pushes around these little objects, and it's also operating this video game here, right? So here the action space is text. So here the model or the agent framework is outputting text tokens. So you can see here the output is text, but the action space or action token output looks like this, right? So we saw this in yesterday's paper too, but as soon as you have different types of tokens, whether they're visual tokens or text tokens or speech tokens, you have to be able to distinguish that. So usually what people are starting to do, and we've seen this now in a couple papers, is they create these start text, start vision, end text. So they kind of explicitly denote the beginning and the end of a different modality of tokens by creating these new type of tokens. So these are new type of tokens, and then you can see here the action token. So there's a specific token for locking on, a specific token for melee attack, a specific token for left rotation, whatever 214 this is, right? So you can see this is in action space tokens versus this one here this is also action space tokens, and then this is text tokens. So this is where I say that I feel like this is a little bit unnecessary in terms of complexity. I feel like eventually we're going to get to a point where you don't need these special tokens that need to be defined for every single video game, or every single video game is going to have a different set of action tokens. So probably what's going to end up happening is that the foundation agent will be so good that it'll just output pure text tokens, and then those text tokens will be consumed and turned into actions by something that is kind of just a generic heuristic, maybe another language model. But okay. The reason I brought this up, though, is because, so this is the action. Here's your transformer model. So you can see this transformer model consuming a sequence of tokens. You have some blue tokens, which represent text tokens. You have some of these orange tokens, which represent action tokens. You have some green tokens, which represent visual information. Obviously, you have to pass these through different types of tokenizers or encoders. This is, for example, a visual encoder, which is usually some kind of pre-trained vision model. The agent tokens, these are the ones that have to be done per task. And then the tokenizer for text is probably just some generic text tokenizer. But I also wanted to talk about this. So this is a paper called LEGO, Language Agents with Chain of 3D Thought for Generating Unconventional Objects. And this is kind of a weird idea, but I thought it was a little bit cool just to show you how general GPT-4 Vision and GPT-3 are, or GPT-4 are, where what they do in this one is that they basically say, okay, when you're sitting there with DALL-E 3 and you give it a weird prompt, such as a chair with 5 legs, right? Early versions of text-to-image generative models such as Stable Diffusion or DALL-E 3 have difficulty in combining multiple concepts in one image and mix up different attributes. This difficulty persists even after repeated attempts to adjust the outputs with human feedback. So, for example, here it generates this and you say, that's not 5 legs, please make the chair with exactly 5 legs, and it doesn't understand that, right? We were seeing examples where people are saying, generate an image of a room for me that has no elephants in it, and it has an elephant in it, because you're literally putting the word elephant in there, so it's kind of confused about exactly what you want. So in this paper, they have this crazy idea where they basically train an agent that lives in Blender. So Blender is like a 3D design program, right? It's basically a program where a 3D artist will sit there and they'll basically create objects using primitives, right? So the primitives are things like cubes or cylinders or cones or spheres. And usually real 3D artists aren't actually building things out of cubes and spheres and stuff like that. They're doing more kind of complicated things. A lot of people are good at like modeling, so they have these like almost like virtual clay, and they like model it, and there's a lot of skill in that. But you're now seeing that a GPT-4 Vision combined with GPT-4 can effectively zero-shot simple Blender or 3D artists. So these things are AGI. Like, what other evidence do you need? Like, this is a zero shot controlling Windows, zero shot controlling a Mac computer, zero shot controlling robots, zero shot doing 3D asset and art design, zero shot. This is not exactly zero shot because they're training these special encoders for the action tokens, but we're there. You know, it's like that is such a broad set of tasks that these state-of-the-art LLMs, despite being trained on only text, are able to zero shot. I don't know. That is just, to me, it's like, what other evidence do you want? This thing is basically AGI. Okay, but then basically they ask GPT. In this case, it's using the Python API. So Blender has a Python API that you can use to basically spawn objects at specific locations. And they say, okay, write a Python script for me that generates a table, and then it like does it piece by piece, and they like occasionally interrupt it, look at it with a vision language model and say, okay, does that actually have 5 legs? It doesn't have 5 legs. Okay, remove one of the legs, and so on. And then once they actually get the mesh, they render it into an image, feed it into ControlNet. This is the part that will definitely go away. This seems kind of unnecessarily complicated, but just the fact that you can have a GPT-4 just design things from scratch like this in Blender is insane. Right? And you can see that here's the kind of full loop, which again is complicated. And with pretty much all of these papers, these loops are just too complicated. These abstractions, I shouldn't say the loop is complicated, because the loop can be quite simple, but these abstractions are just too complicated right now. Like, look at these. You have like all this unnecessary memory, and you have a local plan versus a global plan. You have this limited action space. That type of stuff is all going to go away. I think all this complexity goes away, and you just end up with, right, once you get to GPT-5, GPT-6, GPT-7, I don't think you're going to need to have explicit memory because the context length will increase. I don't think you're going to need to have a specific action space and specific action tokens, because you'll just be able to output text tokens and then go from the text tokens to actually controlling things. So I think it's just going to be one zero-shot VLM or MLM, MMLM. Question from Adam. I understand you need to find pictures from a party that are in the comment. Can you narrow down the time frame? Was this the last year, month? Hello, I'm an agent for user UUID. I don't know what's going on, Adam. I think you're like LARPing and I can't pick it up. Okay. Action modeling loss minimizes the negative log likelihood of each action token. Condition all prior information, including all text tokens, prior visual tokens, and prior action tokens. So basically, this is the same loss that you have for next token prediction in a standard language model, right? You're reducing this negative log likelihood. It's basically a classification loss over all possible tokens at each token. Pre-train, this is actually kind of an interesting thing here at the end. So in the conclusion of this foundation model paper, they say here, by pre-training on a mixture of robotics and gaming data, our model is effective in modeling actions across a variety of domains, even showing positive transfer when fine-tuning in unseen domains such as healthcare. And we've already seen this before, right? So I think in other language model papers, we saw how if you add a bunch of coding information or a bunch of coding data into the pre-training, the model gets better at other tasks that are potentially unrelated, right? So we've seen how there's this idea of positive transfer, which means that the learning that the model has done on one domain makes it better at a separate domain or a separate task, right? And now we're seeing the same thing happening with these agents, right? Where basically, if you have an agent system and you're fine-tuning specific parts of that agent system on one particular task, it's going to get better at other tasks. So if you can get better at healthcare by just playing games, there's a lot of games to play, right? And it changes the situation, because in some of these domains, such as healthcare, you're going to see an attempt by the current incumbents to basically slow everything down, right? So people in healthcare, they're going to try to limit the progress of AIs in healthcare by limiting the access to healthcare data, right? So if you're representing the collective interests of medical doctors, you don't want these AIs to come and replace you. So one way to do that, one way to slow things down, is to put a bunch of regulation on the ability to get healthcare data, right? So if you can keep all that healthcare data in a vault and you never let the AIs train on it, you're thinking, okay, well, I can slow it down. I can prevent these AIs from taking my job because they're just never going to get any of this healthcare data that I have stored behind lock and key. But what we're seeing is that it doesn't fucking matter, dog, because the AIs are going to get better at being a doctor than you just by playing games, right? The AIs are going to get to superhuman level by just generating their own games, playing their own games, right? This kind of self-play loop that we're already seeing happening. We saw it in some of the Google DeepMind papers where they have self-play loops for coding and self-play loops for math, right? And we're seeing how they're basically they're already at superhuman math levels and superhuman coding levels. It's just that humans have a little bit more flexibility, so we still have that. But those models that are in self-play loops for domains such as math and coding, you're going to see the same thing for gaming, right? So the same kind of situation is going to happen where people are going to start putting these agent-like systems inside self-play loops where they play a bunch of different games, like hundreds of different games, and at the other side of that self-play loop, you're going to end up with a agent system that isn't just good at games, it's good at everything, right? So I think that's an interesting thing to think about, where it doesn't matter that the regulatory environment is going to try to shield certain things such as legal and healthcare by protecting the data, because whether they release that data or not, these systems are going to get intelligent regardless, just because they already have enough to train, they have enough to learn from, because games. I'm not a doctor, but I do play one on the training simulation, exactly. Okay. So agents are here. They're really good at zero shot. You can fine-tune them if you want a little bit. You can, right now, make up for the fact that the zero shot isn't perfect by having these kind of complicated frameworks where you're doing this kind of retrieval augmented generation. You're keeping repositories of tools. You are specifying, you're grounding the actions or grounding specific actions in a vision language model by annotating images, and you're explicitly creating action spaces such that the output is more narrow. But I feel like all of that complexity that I just described there, all of that's going to go away, and we're effectively going to just be able to zero shot any kind of agent-like task with your standard vision language model, multimodal language model. Okay, what else do I want to show here? So I did want to show some of the performance. I think they have some performances here. Yeah, so this is kind of further comparison or further evidence to what I'm talking about, right? So performance achieved by UFO, which is their whole agent system on Windows Bench. So I don't really know what Windows Bench is. I think it's just like a benchmark for Windows tasks. So just some generic, like how good can you open up these four things? And this is the important thing that you want to look at here. It's GPT 3.5 versus GPT 4, 24%, 42%, 86%, right? So all this complexity that they're doing here, the reason they have to add all this complexity is because it doesn't quite work well enough, right? But if you just look at this, the difference between GPT 3.5 and GPT 4, look at that success rate difference. You're doubling that just by making the LLM better. So what happens when you have GPT-5, right? What's going to happen to that number? What happens when you have GPT-6? What's going to happen to that number? At some point, the GPT-7, GPT-8 is going to get so good that you're not going to need any of this shit here. It's just going to, you're just going to zero shot it, right? So all we have to do is wait. All we have to do is wait for Sam Altman to make his NVIDIA competitor and we have 10 times more GPUs, 100 times more GPUs. We'll train models that are 10 times bigger on 10 times the amount of data. We'll put them in these self-play loops where they basically just sit there and play video games over and over and over and over and over again, generate new video games, and then play those new generated video games over and over and over and over again. And we're going to get to superintelligence. And this superintelligent agent will not be task specific. It won't be limited to operating your Windows computer or operating your Mac computer. It'll literally be a generalist superintelligence, which means it'll be able to do anything, right? You deploy it in a hospital, and it's making better recommendations than the doctor. And I don't know what happens when that happens. I feel like one thing that I've been thinking of is that, right, whenever we talk about the singularity, right, people talk about the singularity as if it's like a single point, but we've already gone through a singularity, right? This is important to realize, is that think about now when you go into a public place, whether it's like a restaurant or a subway or something like that, everyone is on their cell phones, right? Everyone's just sitting there on that little cell phone, just scrolling. That's completely different, right? So 10 years ago, you would go into that same subway, into that same public place. Nobody was on their cell phone, right? So over 10 years, we've already gone through a weird singularity where everyone is now acting differently and our world is completely different, right? So you've already experienced what going through a singularity feels like. But I don't feel like there was a single point in the past 10 years where I was like, this is the day that we transitioned from a non-cell phone world into a cell phone world, right? It just kind of like, it kind of happens in the background. You don't even realize it. And I think that the same thing is going to happen with these AI agents, where it's not going to feel like there's a specific day where suddenly everything transitions, right? So this idea of the singularity as like a specific moment in time, I think that's incorrect. But it's going to be the same thing where 5 years from now, you're going to be sitting there talking to your computer, and you're going to realize to yourself, holy shit, it's been 2 years since I've used a keyboard. Right? I came to that conclusion myself. I was thinking about it, and I was like, when's the last time I wrote something by hand? Do I even know how to use do I even know how to use a pencil anymore? Right? So this is going to happen again, right? We're going to go through another one of these transitions where the world is going to be completely different, but there's never going to be a single point where you suddenly feel like everything changes. But then once you get 5 years from now and you look back, you're going to realize, holy shit, the world is completely different. But how will I use Vim? You won't, right? The keyboards are gone, man. Just think about it this way. All the time you spent learning how to type really quickly, none of that's going to matter. I'm already trying to transition from that. So already, at least when I code and when I, for example, journal, or when I try to do things on my phone, I'm trying to get better at speech control. So it's difficult for me because I'm someone who's typed, right? It's like I grew up typing things. So I'm a very fast typer. I'm good with my mouse. I can click on things, but those are skills that are disappearing, right? And I think the skills that you want to actually get good at are being able to say things concisely, right? So if any of you have tried to do speech recognition, one of the things that is annoying is that you have to know what you want to say, right? So once you start to do this transition yourself, you're going to realize that you pause a lot, you'll say the wrong word, and it's a little bit of a difficult transition. The same way that the boomer generation, right? They're very good at writing. They probably have better handwriting than we do. But then once they get on a keyboard, they look terrible, right? And they don't know how to type. So the same thing is going to happen to our generation, where we're really good on the keyboard, but then we're going to be clumsy when we're talking to the robot, versus the Gen Z people and the people in the generation under them. They're going to be way better at talking to the robot, right? They're going to be very good at just kind of like, this is exactly what I want, and I know exactly what to say, and the minimum amount of tokens, and then you do it for me, computer, right? Versus we're going to be sitting there being like, where's the escape button? Can I just type in my password? I just want to type it in. And the robot's like, I can't, I don't have a keyboard. I can render one for you in your VR headset if you want to use a keyboard. So I don't know, be prepared to be the old guy. Okay. So I think I went a little bit too far, but I want to bring this back a little bit more technical. So The transition that I had in mind was here in this paper here. This is the foundation model paper. I was talking about this idea of action tokens, right? And we know that kind of we're weaving in all these tokens together now, right? We're using these kind of start action token, end action token, start vision information, end vision information, and that's allowing us to weave in together all these different tokens such that a single transformer model can consume them. But can we do better than that, right? And I think this is what text tokens look like. I think I showed you guys this before. But one interesting kind of point here. So kind of the talk of the town is this guy here, Karpathy, very famous deep learning researcher. He recently left OpenAI, right? So he left OpenAI, and then almost immediately he starts, look at this, 52 minutes ago. He's doing this as we're talking, 1 hour ago, 11 hours ago. What is Karpathy working on? What did he choose to work on the second he left MIT? He chose to do a minimal, clean code for the byte-level byte pair encoding algorithm commonly used in LLM tokenization. So basically, Karpathy was like, okay, we need to fix the lowest level problem. The lowest level problem is, what is the tokenizer that you're going to use for text, right? So if what we're saying is that everything is going to become these text tokens, right? Even here, whenever you take an image and you feed it through this vision encoder, usually you have these projector layers which learn how to basically turn these vision tokens into something that is almost like a pseudo text token, right? So the purpose of this projector here is to transform what's coming out of this pre-trained vision encoder into something that looks like what's coming out of this text tokenizer, right? So I just think it's kind of interesting that Karpathy decided to basically work on the lowest level stuff, right? At the foundation level, we're going to need to tokenize information, and tokenizing that information, there's different ways of doing it, right? BP is one way where you're basically going through your entire training data set, and then you're looking at which characters appear next to each other. So actually the way you start, for example, I think in this one, given a list, merge. Yeah, so it starts with this. So the default vocabulary size is 256, which represents all the characters, basically the raw characters that a computer has, right? And then over time, what this tokenizer is going to do is it's going to basically kind of discover the best possible tokens, right? It does some statistical magic, but it basically discovers, oh, okay, you see the letters D, E, and F. These letters almost always appear next to each other because there's a bunch of coding data in my text or in my pre-training data. And because of that, I'm going to make a new token, which is the DEF token with a space in front of it, so that rather than this being 4 tokens, as it would be at the beginning of the min-BP process, at the end of this min-BP process, I'm going to basically have a much larger vocabulary. So the min-BP starts with a vocabulary size of 256, but by the time you get to the end of this process, usually the vocabulary size that you get for language models or text is like around the 10,000 or 30,000 different possible tokens, right? So I feel like that's probably going to change, right? So all the LLMs right now, including apparently GPT-4, he gives you a little hint here. Did he actually change that? GPT-4? Yeah, this was introduced in GPT-2 and continues to be in use as of GPT-4. So GPT-4 still uses the same kind of tokenization process that all these LLMs use, where you're basically using BPE or something like sentence piece to basically grow a vocabulary of usually around 10,000 to 30,000 possible text tokens. But I think there's an opportunity here to make this more simple and more generic, right? So I think we're probably close to moving to a type of token that is like there's a million possible tokens, right? So the transformer model, when it's auto-regressively predicting the next token, rather than picking from 1 out of 30,000 possible text tokens, or rather than picking from 1 out of whatever, like 50 or maybe 100 different action tokens, it's basically picking out of 1 out of a million tokens. And those million tokens are like as close as you can get to like the rawest level information in your computer, right? So like, I don't exactly know what that means, but I feel like there's an opportunity here, and it's no coincidence that Andre's working on this where, hey, let's figure out a tokenization vocabulary that isn't just limited to text and that also is just an order of magnitude bigger than what we currently have, right? So we know that scaling things makes things better. So rather than 30,000 tokens, let's try 100,000 tokens. Let's try 1 million tokens, right? And I bet you that'll probably work better. I don't have any evidence to show that, but I think that that's probably the first. We start at the simple stuff. Start at the lowest level, try to fix that problem, and then let scale fix the rest. Why do the space tokens have different colors? So the space tokens have different colors here because they're different tokens. So the colors here don't mean anything. So here, the purple doesn't mean anything that this is purple, right? The colors are just to let you know which token, where the token separations are. But here, for example, you see these three, there's a green space. What this is saying is just 3 space tokens. So all 3 of these tokens are actually the exact same token. It's just they're colored different colors just so you can see that there's a bunch of different tokens here, but the color doesn't mean anything, right? So here, the def token is blue. Here, the def token is yellow, but it's all the same token. Bytes instead of tokens. Yeah, something like that. I feel like to me, it's like going to go at a lower level. I don't exactly know what that lower level is. I don't know if it's like literally going to be, maybe rather than a larger vocabulary, you actually end up with a smaller vocabulary, right? Maybe you end up with something that's a little bit closer to the 256 tokens that you see here, right? Maybe in 2030, when we look at a giant LLM or multimodal foundation agent model, maybe the vocabulary that it's using is literally just only of size 256, and it just that's what it's outputting. But I don't know. I think it's the other way. I think if anything, the vocabulary size will increase. Okay. There is provably an optimal vocabulary size for a given problem context. Yes, but whenever you're doing that, it's optimal with respect to that given problem. I'm saying that rather than constraining the problem and then coming up with a set of tokens which are optimal for that problem, which is what they're doing in this thing, right? I think that the better thing to do would be to create a set of tokens that work for every single problem, even if they're not necessarily optimal for that problem, right? And we already have evidence of that, right? So if you think about it, the text tokens, these are the same text tokens that are being used to generate code that are being used to generate Shakespeare, right? Or a haiku, right? So whenever you're sitting there and you're querying your language model and you're saying, generate a Python function for me that does blah, and then you're saying, generate a Shakespeare haiku. I don't know if Shakespeare did haikus, but the language model is predicting the next token and picking from all possible tokens, and all those possible tokens are the same set. So it's the same vocabulary, whether you're doing code or whether you're doing Shakespeare. And it works pretty well, doesn't it? Right. So that's what I'm saying. I'm saying make it more generic rather than, in that case, right, imagine having a different tokenizer for code and a different tokenizer for Shakespeare. It would just make it more complex for no reason, right? Just have the same tokenizer for all text. And I think you just got to extend that idea a little bit further, have the same tokenizer for everything. Okay. So that's kind of the agent part. I did want to talk about these two things because these two papers they're not exactly related, but they're close. And I think they're interesting because they kind of show a little bit of magic here. So we have 2 papers here. One is a DeepMind paper, and this one is a Tencent paper. So Tencent is a giant Chinese tech company. 3rd February 2024, and then this one is 15th of February 2024. So this one's called Chain of Thought Reasoning Without Prompting. So few shot or zero shot chain of thought prompting. So zero shot means doing something in the first try. Chain of thought means that rather than the LLM basically outputting your answer directly, you give it or you can instruct it to do this, but basically you allow it to kind of reason, right? And by reason, it's just like explicitly thinking out loud. So it's kind of like saying what it thinks out loud, and then that's chain of thought. And there's like a huge variety of different types of chain of thought, and people have kind of gone all the way to the ends of the earth with different variants of chain of thought. Can LLMs reason effectively without prompting? Our finding reveals that intriguingly, chain of thought reasoning paths can be elicited from pre-trained LLMs by simply altering the decoding process. The decoding process is when you're actually predicting the next token, right? So when you're actually going through here and you're like, okay, class, bank, what's the next token for this, right? And then it has to pick one out of the 30,000 possible tokens to put there. So in conventional greedy decoding, you're picking the best possible token, versus in this paper, they're going to be investigating the top K alternative tokens, uncovering chain of thought paths that are frequently inherent in these sequences. And cutting to the chase here, proposed chain of thought decoding substantially outperforms the standard greedy decoding. Okay. So let's go to an actual example of this to kind of illustrate exactly what's going on. So let's say you have a question and you're asking your language model this question. You give it, I have 3 apples, blah, blah, blah. My dad has 2 more apples. How many apples do I have in total, right? So the language model is just saying, okay, what is the next token that I'm going to output here, right? So out of all 30,000 possible tokens, I'm going to run a classification on all 30,000 possible tokens and then pick the next one that I'm going to say. So here's a visualization. I'm going to show this later, but it's just showing you, for example, let's say your vocabulary was only 9. So let's say you had 9 possible tokens that you could pick from, right? When you autoregressively predict the next token, what you're doing is you're basically saying, okay, what's the probability that the next word is 0? What's the probability that the next word is 1? What's the probability that the next word is 4? And so on, right? So you can see how here it's obvious that the next word is probably 9 because it has much higher probability than all the rest, right? It's kind of like a classification problem. So if you were doing greedy decoding, you would just pick this one. You would pick 9 because that's the highest probability next word. So here what they said, okay, what are the other ones, though? So we know that the top one is 5, but what are the other ones? So that would be, for example, this one here. So the next top one would be 9, then you would have 7, then 0, then 4. In this case, this is more complicated because it's text, right? So there's 30,000 possible tokens, but it's saying, okay, 5 is the best. The next one is I, then we, you, thee, right? And what most people do is greedy decoding, and in that sense, you would just say, okay, well, the next one is 5. Okay, now that I picked 5, what's the token after that? Apples. And it turns out that in some situations, or most situations, if you just do this greedy decoding, you sometimes get the wrong answer. But if you look at some of the other answers, if you were to go into that, you would end up with the right answer, right? So that's kind of an interesting situation there, right? Where now, if you, in the way that they say in this paper, if you kind of investigate the paths or the decoding kind of chains that start with a chain of thought, here's a chain of thought right here, right? Ultimately, you'll get to a better answer, right? So the reason that your language model got this question wrong is because you're just greedy decoding, and the greedy decoded answer, which is kind of like the instinctual answer, is incorrect. But if you were to just given it some space and let it think about its answer, you would have eventually ended up at a better situation. And not only is that the case, but here they also say that higher confidence in decoding the final answer when chain of thought reasoning path is present. So you see how this 8 is a darker color than this 5? You see his uncertain versus certain. What that means is that if you were to actually look at the probability of this token, right? So if you were to actually look here, it's a very certain to be number 9. But if you were to actually look at the probability of this token 5 here and then this token number 8 here, right? There's much more confidence in this 8 token than there is in this 5 token. So that's kind of interesting, right? So considering alternative top K tokens, where K is like how many you're considering. And if you've ever, so for example, you guys, greedy decoding, even though I'm saying that that's what people normally do, that's not actually what people normally do. What the type that you're normally used to is called temperature sampling. And in temperature sampling, what you're doing is you're basically sampling from this distribution. So rather than saying, okay, well, out of 9 possible tokens in my vocabulary, I'm picking token number 9 because it has the highest probability. That's what greedy decoding would be. In temperature-based sampling, what you're doing is you're basically saying, okay, well, I'm actually going to almost like think about a dice that has these probabilities. I'm going to roll that dice, and most of the time I'm going to get 9, but some of the times I'm going to get 7. And that's why a language model has weird behavior, right? That's why you don't get the same answer every time you prompt something with a language model, is because you're not actually doing greedy decoding and picking the most probable answer. If you were to do greedy decoding and just pick the top token every time, you would get the same answer every time, right? So that's not your experience. You as a person are used to this kind of temperature-based sampling where you sample, so you usually end up with similar top answers, but you don't actually, because sometimes you might pick this 7, right? And if you pick that 7, you're going to end up on a totally different train of thought, which is what's happening here. And then in this paper is all about kind of coming to the realization that a lot of times these language models are correct if only we were to pick slightly different initial tokens, or what they call alternative top K tokens. Okay. So this is kind of I don't think this is worth going into. Selecting the decoding path based on its length with the intuition that longer decoding paths likely contain more chain of thoughts. So this is kind of the idea that the more tokens you give it to reason, right? The longer your chain of thought, the more likely the answer is. And there's been plenty of other papers that have basically proved that the more you let the model kind of like output tokens that only further explain the problem or kind of act as a chain of thought, the better it does, right? That's why the one trick that everybody uses where it's like, think about this step by step, right? Whenever you type in think about this step by step, you're basically altering the path that it's taking, and now it's going to basically output a bunch of tokens that are having to do with thinking about it step by step. And then once you finally get to that end of that paragraph where it's thought about it step by step, it'll much more accurately and with a higher confidence predict the right answer out of all 30,000 possible tokens. This is the standard token sampling that you're used to, right? Temperature sampling, where it samples, found that is much less sample efficient compared to our COT decoding procedure. The first token is samples based on the model's probability distribution, heavily influenced by the model's tendency to output a direct answer rather than taking a less direct route. So maybe I'm going to show you why I pulled this up. I've shown this example before, but like what exactly is the temperature doing? So what the temperature does is so here, the softmax, this is the equation for the softmax. You're putting in your logits, which are the raw numbers that come out of your language model, and then you're putting them through the softmax in order to get this basically probability distribution, right? Which is telling you this is probably the one you want, this is not the one you want, but here's the difference between them. As you increase the temperature, so whenever you increase the temperature on your LLM, what you're doing is you're basically increasing or decreasing the difference in these probabilities. So basically, if you're doing temperature sampling, you see, if your temperature is very low and you're doing temperature sampling, you're almost always going to end up sampling the 9. But as you increase the temperature, it becomes more and more random because the probabilities become more and more equal, so that you're about equally likely going to pick the 9 as all the other ones, right? So that's why the temperature makes it feel like your language model is more random. It's because it's just each individual choice of token is more random. Okay, so in this paper, they do this on Palm 2 and then Mistral 7B. What do we got here? Palm 2 pre-trained, Palm 2 instruction tune. So the instruction tune ones are the kind of like the chatbot ones. Pre-trained are just like raw. This is the models that we wish we had. Greedy versus this COT decoding. Look at this, twice as much performance. These are different benchmarks. I think these are math benchmarks, GSM-8K and then multi-arithmetic. So 2 different math benchmarks. And the difference between greedy decoding, right, which is just picking the one that has the highest probability, you have quite a significant difference there between this chain of thought decoding, right? The chain of thought decoding is this idea that they're doing here where they're basically saying, okay, what are the top 5? And then kind of like go down that chain and then see if you get the final answer that's higher and better, or higher, less certainty. Use the certainty of the answer or the probability of that token given previous tokens, right? But compare it to the different paths. It seems to not matter as much for these larger models. So if you look at this, 27% improvement for greedy versus chain of thought on this small sized model, but then the large model, not as much of a difference. Granted, it's also because as you get to closer to 100% on these benchmarks, it gets harder and harder and harder. So there's kind of like an S curve for the difficulty of this benchmark anyways. But I think it's kind of interesting that you don't necessarily need to look too much into the chain of thought as these models get bigger. So potentially this whole chain of thought becomes obsolete once we have big enough models. But right now, it seems like it's pretty good. Higher values of K typically result in improved performance, where K is basically how many of the top you're considering. Top 1, K equals top 1 would be greedy decoding. So here, top K tokens for decoding paths. If you're considering the top 10 possible tokens, which isn't even that much, right? There's like over 30,000 tokens in these vocabularies here. So the top 10 versus the top 2, really not that much of a difference, but you see how it does make a difference in accuracy. And you see how the larger models plateau a little bit more than these smaller models. Another noteworthy observation is that chain of thought decoding can better reveal what LLM's intrinsic strategy in solving a problem without being influenced by the external prompts, which could be biased by the prompt designers, right? So what they're saying there is that people very quickly figured out this trick where if you ask it a question and then you say, let's think step by step, it gets into this kind of chain of thought mode. And then by getting into that chain of thought mode, it's going to spend a bunch of tokens thinking about it, and then by spending a bunch of tokens thinking about it, it's going to end up with an answer that it has higher certainty in. So we figured out through prompt engineering how to kind of put the model into this mode where it's going to do what you want it to do in order to answer the question. What they're saying here is that as we get better at this chain of thought decoding, where we're looking at all the possible decoding paths it could go into, and then exploring all those different branching paths, we don't need to get as good at prompt engineering, right? So right now, being good at prompt engineering and knowing exactly kind of what tokens to put in there to kind of bias the chain of thought in a particular direction is very important, right? And you can get much better performance if you are good at prompt engineering. But as we start getting better and better at this kind of chain of thought kind of exploration, we're not going to need to be as good at prompt engineering because we're going to be able to kind of explore down all the possible paths that the language model could have gone down on, right? All these works still require chain of thought prompting in order to generate the chain of thought reasoning paths, while our work completely removes chain of thought prompting. In addition, these existing works focus on searching and verifying the steps, while our work purely searches in the decoding space on the token level, right? So kind of what they're saying here is that these existing works, they're not necessarily talking about the stuff that we were looking at here, but it rhymes with that kind of stuff, right? Where if you look at some of what's going on here in these agent papers, there's a lot of chain of thought that maybe is unnecessary, right? So the reason you're creating this complicated system of language models that are all kind of acting with each other in this framework is because these language models are basically changing the probabilities of the tokens, right? So by having all these tokens here, all these text tokens, you kind of ensure that these tokens here are good. And by having these tokens here, you kind of ensure that these tokens are good, right? So we're in a paradigm right now where in all of our frameworks, we're doing a lot of explicit chain of thought, right? Where we're basically using prompt engineering tricks to force these language models into these very long chain of thoughts so that we can then force it into more chain of thoughts to then get to the answer that we want. But maybe we don't really need to do that, right? And maybe rather than kind of explicitly creating these chain of thoughts via prompting, as we're seeing in all these agent papers where we're kind of forcing it to create these chain of thoughts, maybe we can get most of that by just basically looking at the actual raw logits and the raw probabilities and saying, okay, well, let's just not greedily decode and then put that into the context for the next language model. Let's actually look at the decoding that could possibly happen for this specific question and then figure out which of those is the best one, use that one instead, and then maybe we don't have to be creating all this like filler content so that we can guarantee that future LLM that are using that as their context get good performance. So I kind of thought that that was a pretty powerful idea, right? This idea of like kind of searching through the decoding space, right? Our work purely searches in the decoding space on the token level, right? And that kind of rhymes with this Rich Sutton-Bitter lesson, right? Where the two techniques that scale very well with scale are basically learning and search, right? Where search is one of these things where it's like, if you can 10x the speed at which you search and the amount of data with which you search in, that's a very easy way to continue to improve as you continue to scale. So if we can figure out how to basically make models much better by creating this search problem inside the like possible chain of thought decoding paths, that's a completely orthogonal path of improvement, right? And I think they mentioned that in this paper as well. Presidents, co-founders, I think they say it in the, let me go to the conclusion here. Exploration, alternative decoding paths incurs additional computational costs. Exploring alternative Top-K tokens reveals the natural existence of reasoning paths within these models. Our empirical observations highlight that the presence of a chain of thought reasoning path correlates with increased model confidence in decoding its final answer. Based on this observation, we introduced chain of thought decoding. There was like a particular sentence here that I was looking for, but the sentence I was looking for is that this is separate from all this shit here, right? So it's like, it's not either or. You could do both of these. You could take any one of these agent papers and then basically apply this idea to it, and it'll probably perform better. So let me take a sip and then I'll go into this paper. Dude, you guys are going crazy on the chat. Like, what is going on here? Talking about parabolas doesn't help plan basketball play. Maybe it does, I think there's a lot more transfer learning than people think there are. I think that maybe not, like, do you think your average basketball player would be better than your average person at like questions involving parabolic trajectories? Maybe. I think it's like the problem is that type of learning for humans, like the transfer isn't quite there, but for AIs it is, right? So as they mentioned in this paper, I'll bring it up again, but this transfer is crazy, right? The transfer of robotics and gaming data transferring to good domains such as healthcare. I think that's like the most crazy transfer, right? Like what is going on inside these games that you're getting better at healthcare? I guess the definition of healthcare to them is this like weird, like, what is the human doing? But patient is awake and calm. Maybe if you play enough Minecraft, you can eventually diagnose cancer on the first shot. Question from Beyond. Would training or fine-tuning on millions of synthetic conversations that are chain of thought build any of the capability into models in a way that would go in and reverse engineer the differences? Yeah. Yes. The answer to that is yes. So nobody's really proved this, but there's a lot of ideas that are starting to get close, right? this is the idea of kind of self-play, right? Where we know that self-play works for games like Go and chess, right? Where when you're playing a game like Go and chess, there's only a limited amount of training data at the very highest level, right? There's a limited amount of Grandmaster versus Grandmaster games, and you can train on those, and you're going to get a level that's Grandmaster. But then people figured out, okay, we can make them play each other, and in that way generate even more data, right? So the amount of data that exists for Grandmaster Go games, right, is very small. But if you have Grandmaster Go AIs play each other, you can 10x or 100x that, right? So I think there's going to be, and we're seeing that you can kind of do this with math problems and coding problems, right? So in math and coding situations, you can generate, basically, you can have LLMs that generate a coding problem and then LLMs that solve it, and then that is a way to generate, in a self-play kind of loop, a bunch of coding data, and then when you add that to the pre-training corpus, you end up with a coding AI that is better than it was before. So this self-play loop does work for games, and it does work for code. It's not entirely certain whether it works for text and reasoning, but in my mind, I feel like it is, right? I feel like it's probably going to be the case that the AIs of the future that are superhuman at reasoning, they're not going to be trained on reasoning conversations that were done by humans. They're going to be trained on these kind of like reasoning debates for AIs, right? So think about it this way. If you had 10 different AIs and you trained them all on different physics textbooks, and then you had all 10 of those AIs trained on different physics textbooks arguing with each other about physics, and then you took all of those arguments and conversations between those 10 different AIs trained on 10 different physics textbooks, and then trained an AI agent on all of those textbooks, and then also all the conversations that were generating in this kind of like self-play debate between all those AI agents, it would probably be better than the AI agent that is only trained on the textbooks, right? So I haven't seen that evidence myself, but I feel like that has to be true, right? It has to be true that at some point you can create a self-play loop where it's basically just playing this generic kind of debating, reasoning word game, and that is enough to basically then transfer into other things, right? So this AI that just sits there and argues about physics with itself, when you ask it to do chemistry, it's probably going to be pretty good at chemistry, even though the only thing it's done is train on a bunch of data of itself arguing with itself about physics. I don't know. Yeah, zero-shot cancer treatment through Action Agent Minecraft self-play. And I think maybe part of the evidence I can use for this is that we did that as humans, right? So if you think about humans as a collective kind of hive mind, we got better and better at science through basically just talking to each. So it's not like we're smarter than the physicists of 1700s or the 1800s or the 1900s. It's that we got to train on the arguments or papers that were generated by the 1800s physicists, and then the 1900s physicists got to train on that, and then the 2000 physicists got to train on that. So it's like, it seems to me like you can use logic in order to basically create the training data required to train the next level of logic, right? And the fact that our civilization progresses and technology advances is literally proof that you can do this, that just through having a bunch of people sitting in a room talking to each other and arguing, that's a way of creating the data required to get to the next level of people who can then argue and create the data, right? I don't know. Okay, let's talk about this paper here. More agents is all you need. This is Tencent. So if this paper here was basically, okay, we can actually look within a single language model itself and look at all the different tokens and all the different probabilities at each individual token, and then from that kind of investigate the paths that result in the right answer with higher confidence, that's a way of basically getting more juice out of a single language model. In this paper, they have a different approach. In this one, they're basically going to have multiple LLM agents in a debate format. So basically, simply via sampling and voting, the LLM performance scales with the number of agents. So gonna cut to the chase here. I think there's one table here, but GPT-4 or accuracy scales with the ensemble size. The ensemble basically is just how many LLMs are in this system, right? So you have a bunch of LLMs that you ask a question, but then rather than that question going into a single LLM, it basically gets sent to a bunch of different LLMs. Each of them gives you their answer, and then you take all the answers and then pick the one that has the most in common with all the other answers. And here, the majority voting, this makes it look easier because it's just, oh, this is orange, and blue. But really what's happening is you have a similarity function. So you can envision that this LLM agent outputs a little paragraph of text. This one outputs a little paragraph of text. And this paragraph of text, if you feed it into some kind of, another language model, it creates an embedding. Feed that paragraph of text into this language model, it creates an embedding. You can then compare those two embeddings, and the final one is the one that has the most in common with all the other ones. So it's a little bit fuzzy here, right? Because I don't necessarily like this similarity score. Makes it a little sketchy, right? You can envision a situation where, for example, like the length of the response might result in a higher similarity score, and that might mean it blah blah blah. Like there's some nuances here, but you know, the basic idea is that, okay, rather than just using one LLM, use multiple LLMs and then just use majority answer to determine the final answer, right? And the cool thing is that you don't even necessarily need to use the same LLM. And they talk about here ensembling frameworks based on multiple heterogeneous LLMs. And this is kind of interesting because to me it means that what if we end up in a future where rather than having one language model or one AI agent that does everything for you on your computer, you have an ensemble of AI agents. And what if those ensemble of AI agents are heterogeneous, right? So what if Microsoft has an AI agent, and then there's 3 other open source third-party AI agents that you're using, and then all of them are acting together to do what you want, so that every month you can go and say, okay, here's all the different things I did this month, and I had this ensemble of LLMs that were each giving me different answers, and it turns out that this agent here was actually way better than this agent here. So therefore, I'm going to use this agent here. I'm going to clone it and make 2 copies of it so that my little LLM council, my little LLM buddies, right, my little inner friend group of LLMs, now I'm going to duplicate the ones that are good for me, remove the ones that aren't good for me. And I think that would actually be a way to get a lot more control into ourselves, the humans, right? So like one of the ways that this all goes bad is that we basically surrender our control of our agency to the companies, right? People like Microsoft, they basically get all your agency. But if we can figure out a situation where the different agent providers, the different LLM providers are competing to see which one can help you the most, right? That could end up in a situation where now we have all the control, right? So I think that's an interesting way to kind of end up in a future where it's a net positive that you have this competition, right? But I think it might be difficult to do that. Our method is compatible with a broader range of methods such as prompt engineering, including chain of thought and multiple LLM agent collaboration. So you can envision how this LLM ensemble technique would work in combination with this, right? So rather than just saying, okay, well, these different LLMs, one of them might be Llama, one of them might be Mistral, they're going to give you an answer. Rather than just taking this answer here, which is either sampled or it's greedily decoded, do this shit with it, right? Do this chain of thought decoding to get the best possible answer out of each LLM and then do the majority voting. So you could basically combine this paper with the paper that we just read and it would be even better. And I feel like this represents some low-hanging fruit here, right? Like, think about, none of these papers are doing this, right? None of these agent papers, such as this Windows one, or such as this VLM one for the robots, or such as this foundation model, none of these papers are really doing any kind of chain of thought or I think they're doing a little bit of a chain of thought, but none of them are doing this kind of chain of thought, this decoding here, where you're kind of going down the different paths, and none of them are doing this ensembling. So there's an opportunity there. You can take any of these papers, apply these two ideas to it, and probably get state of the art. So if some of you guys are looking for research ideas, that's an easy one to do, right? This isn't even very complicated to implement. So if you're willing to pay for the extra inference that ensembling means, and this chain of thought also requires extra compute because you have to go down all these different paths, but you can get better performance. And the performance is quite good. Here, for example, in table 2, they compare the performance. Again, similar kind of benchmarks. You have different benchmarks for math, chess, blah, blah, blah. But look at this. So if you ask a single Llama 2 13B on GSM 8K, you get a score of 0.35. If you do an ensemble of Llama 2 13Bs, you get a score of 0.59. But look at this. The ensemble of 0.59 is better than the single 70B. The ensemble of 70Bs of 0.74 is better than GPT 3.5 Turbo. So there's no reason this isn't going to scale, right? So basically, an ensemble of Mistral 7Bs is better than a single Llama 2 70B, is better than, at some point, if you have 1,000 Mistral 7Bs, the answer that they give you might actually be better than GPT-4, right? So ensembling should also kind of infinitely scale, which is pretty powerful, right? It means that the quality of your response is no longer limited by some model architecture or something like that. It's now limited by just how much compute are you willing to spend on this, right? If you're willing to ask 1,000 LLMs, you're going to get a better answer than if you're willing to ask 10 LLMs. And it doesn't matter if those 1,000 LLMs are all tiny and not necessarily super smart individually. Together as a hive mind, their majority vote is stronger. And this is another one of those things where I feel like we figured this out as humans, right? So as humans, we already figured this out a long time ago that, hey, I have some ideas as me, a little individual human, and that guy over there has his ideas as his little individual human, and she's got her ideas as her little individual human. But if we all pool our answers together, 3 of us together are smarter than 1 of us alone. And then that's how we created nations and tribes and companies, right? We created these abstractions that are basically these hive minds where 100 humans together is way smarter than just 1 human by itself, right? So the same thing is happening with LLMs, where these ensembles of LLMs accuracy scales with ensemble size, regardless of the different LLMs. So look at this. Ensemble size, 0 versus 10 versus 20 versus 40. So 40 GPT 3.5 turbos gives you a way better answer, almost 10% more accuracy than just 1 GPT 3.5 turbo. There's a little bit of a flattening here, so at some point you kind of get to the max, and maybe if you combined this with this, you would get even better performance, right? But it would be a lot more compute intensive. I think that's pretty much it. I think that's all I had for these two, which is all I had in total. But let me scroll through the chat here, see if I can find some questions here. How is that question from Kalina? How is that different to self-consistency majority vote approaches, different naming? Yeah, so the difference between this and ensemble is it is more similar than it is different. So I think you are correct there, Kalina, that technically if you're using an ensemble size of 40 for a GPT 3.5 Turbo, and the GPT 3.5 Turbo is using temperature-based sampling, really what you're doing is you're kind of almost like explicitly going through the path here because it's all the same language model. So if you're using the same language model, this approach kind of looks a lot like this approach. They're kind of doing the same thing, right? It's like one of them you're actually explicitly going through each of these because you're running this 40 times. And in this one, you're kind of implicitly going through it because you're going into the actual logits and you're comparing the different sizes of the logits and then kind of speculatively looking ahead in those chains. So there are very similar. The difference is that this, you can do it with a heterogeneous mix, right? So you don't actually need to use all of the same LLMs, but in this one, it's only one LLM, so it would be the same LLM. You're looking down all the possible different chain of thoughts that one LLM could do. But ensembling is a more generic idea, and it doesn't it's not like you're going into the one LLM's brain and then kind of looking at all the possible things that it could say. You're looking at potentially a heterogeneous ensemble of LLMs, and they're going to have different ones. That's why I think that you can combine these, right? So you could do this approach for all of them. But actually, now that I say that, you're not going to be able to do this with GPT, right? I think you will, because when Sam Altman presented at the GPT developer conference, he did say that they would give logits, right? He says, oh, we're going to give you logits. And what does he mean by that? What he means by that is that he's going to give you basically this, or specifically this little ZI. But when he says we're going to give you logits, it means that anytime you use GPT, for every single token, you'll be able to say, okay, what was the probability of that token versus other tokens? Right now, you don't know what that is, right? Right now, the GPT just spits out a bunch of tokens. You don't know if this first token was high probability, low probability, and so on, right? But you can do this with open source models because you can actually literally just put a breakpoint in there and then pause it and then see and actually look at those logits and actually get the actual values for those. But in a closed source model where you're interacting it via an API, unless they actually explicitly give you the logits, which is the version of this before you feed it into the softmax, you're not going to be able to do this type of COT decoding. Poor man's MOE. This is different from MOE though, right? This is, in an MOE, you're creating multiple different, we need the transformer architecture. So in a mixture of experts, what you're basically doing is you're inflating the network, right? You're basically making more of these little feed-forward blocks here. You're making a bunch of feed-forward blocks, and then you're adding a little router that goes into different feed-forward blocks. Versus here, right, what you're doing in both of these papers is you're basically looking at what's coming out here in the output probabilities, right here, right before the softmax, it would be the logits, and then after the softmax, it would be interpreted as probabilities. You're going here, and then you're looking at, okay, what are the different tokens and the probabilities for each token? So it's not quite the same as mixture of experts, but not sure about the infinite scale. Saturates before 50 LLM instances. Yeah, you are correct on that. It could be the case that this just flattens out. And it does also seem like the difference matters more for smaller models. So if you look at this, the Llama 2 13B, there's a bigger difference between an ensemble size of 40 and 1 for the Llama 2 13B than there is for the Llama 2 70B, right? So you see how it seems like as these models get more and more intelligence, the difference becomes smaller and smaller. So it could be the case that this stops working at some point. And actually, there's evidence to believe that. So here they say, in Table 2, GPT-4 is used only for comparison with other methods, hence it only presents the single result. So for some reason, they didn't want to tell you what an ensemble of 40 GPT-4s would do. And maybe it's because this number is the same as this number, right? So if you're sitting here and you're about to publish this paper called More Agents is All You Need, and you have these beautiful charts like this, right? It would kind of suck if you get to GPT-4 and it basically gives you a 0.88, right? Because then what that tells you is that, oh, this only really works for small models. So I actually have a secret conspiracy theory here that I feel like they probably ran this for GPT-4. The number wasn't good, and then they decided to omit that number, and they said, okay, let's just not put that number there because it makes us look like shit. It would have been nice to see how an ensemble of GPTs and llamas work. Yeah, I would have liked to see the heterogeneous ensemble too. Okay. All right, you guys are going off, but I don't think there's any more questions. How about I'll give a second here. You guys ask any questions you want. I'm going to sip this coffee, and then we'll summarize what we went over. Okay. So, in today's stream, we went over a bunch of different AI agents. We talked about the future, and we looked at and thought about where is all this stuff going. So, come here. We started off with these two papers here. So, these two papers here are basically self-operating computers. You have one that is by Microsoft and works on the Microsoft operating system, and then you have one by some Chinese groups that works on the Mac operating system. And in both of these papers, they basically create agent frameworks, which are these complicated kind of loops, right? And I keep mentioning this before, but the most simple loop, which is the one that I was taught when I studied robotics at Carnegie Mellon, is called a sense, plan, act, right? Where there's some amount of sensing, then there's some amount of planning or thinking, and then there's the actual acting, right? And that paradigm is, I think, the highest level, right? And all of these are basically types of those, right? So sensing would be things like the observation, which is such as screenshots. It could be the user request, right? It could be the memory, so retrieving specific historical information. Then you have the planning part of it, which is, okay, I'm going to actually, in this case, because it's a language model, it does this kind of internal chain of thought planning where it's kind of like writing out text. Here's my thoughts on this. Here's my thoughts on that. Given those thoughts on that, what do you think the next step should be, right? So that's what planning looks like in the age of VLMs and LLMs. And then there's the actual action. For both of these, it's basically interacting with the operating system. Both of these basically use applications that allow you to programmatically control. So these things have existed for a while now, but you might see better versions of these. I think specifically on this one, they use PyWin Auto, but it's basically like a program that allows you to control Windows via API, right? So kind of very similar to the Minecraft Voyager, where rather than actually moving your mouse around and clicking on things, you're instead sending commands or using tools, where these tools are things such as click, annotate, get text, scroll. So it's basically everything that you can do with a mouse and a keyboard, but via API. And yeah, basically these things are there, guys. They're doing everything. They're using multiple applications. Anything that you're doing on a computer is really not that complicated. And these LLMs and VLMs, there's both of them in there, right? There's LLMs that are going text to text, and then there's VLMs that are usually just summarizing the screenshots. But they're doing these things zero shot, right? So it's not like these guys trained a vision language model on some giant ass data set of people using Windows computers, and that's not what they're doing. They're zero shot taking GPT Vision and GPT-4, putting it inside these kind of like overly complicated agent frameworks, which I think are just going to go away as these LLMs and VLMs get better, and getting really good results with just zero shot. So I feel like as the context lengths get bigger, which we saw with Gemini 1.5, we're already seeing basically 10x improvements in that. We're not going to need to have these notions of like working memory and like retrieving things from memory and then searching your memory to find like all of that is just, you're going to fit the entire history of everything into your context, and the VLM is just going to directly output actions. And that's another thing that kind of is a little bit nebulous right now. So right now there's this concept of actions, right? And we're seeing how the action space is very task specific. So here, the action space on this Windows paper is basically the commands that are available to you in PyWinX, right? So you have an action space that is limited to this Windows OS. Here, in this paper, you have an action space. This is the same kind of idea where you have an agent that is in this case operating within the Blender application, but the action space is also limited, right? It's limited inside the API of Blender, the Python API of Blender. And then the kind of most general agent paper that we read here, where you have a foundation model, they have this same unfortunate idea where it's like, okay, we're going to have a specific action space or action token vocabulary that is going to be limited and specific for each game, right? So for every single game is going to have a different set of action tokens, and that just doesn't seem great. I think that this is eventually going to disappear. I think we're going to figure out some kind of token vocabulary that allows you to do anything with anything, right? So right now, the tokenizers that we use and the token vocabularies that we use are based on these text data sets, right? So they're based on things like code and language. But people like Karpathy are already working on the next generation of tokens, which is the next generation of basically what the output of these models are. So these models, they just output token by token by token by token auto-regressively, and it'd be really nice if you don't have to specify different vocabularies for different tasks. It's just basically always the same vocabulary for any possible task you can think of, whether it's Minecraft or whether it's medical healthcare stuff. And once you do that, once you have a generic model that consumes any type of token, right? So rather than what you do here, where you have a GPT-4 vision consume the screenshots, turn it into a description, and then you have GPT-4 consume the description and do the actual planning in text, I think you're going to have a single multimodal model that consumes all the tokens, right? So kind of like how this one does here. It consumes vision tokens, it consumes text tokens, it consumes action tokens. I think these will be combined together. And it'll just output tokens that work for everything. And I think it'll be like some kind of generic text tokens, maybe bytes, right? Maybe we end up with a very small 256 token vocabulary that is used for everything. But the TLDR here is we're moving very quickly into a world where we have generalist agents that can basically do anything involving a computer. And pre-training on a mixture of robotics and gaming data, our model is effective in modeling actions across a variety of domains, even showing positive transfer in unseen domains such as healthcare. So these agents are not just going to be operating your computer, but at some point, especially if we use the same action space and input space, or observation space as it's called, for all of these agents, they're basically the amount of transfer from all the different tasks is going to compound together, and it's just going to be this giant artificial superintelligence that can basically do anything. Not quite elegantly put, but hopefully you're as excited as I am about this. So that was that. And then the kind of second half of this stream, we looked at these two papers here, which are a little bit different, but they're interesting because they're basically two approaches that could be added on to these agent approaches. And basically what these papers do is this idea of looking at the all the answers that a language model gives you, right? When a language model is predicting the next token, it's picking out of a set of or a vocabulary of possible tokens, and naively you're just greedy decoding, which is just picking the highest probability token. Usually you're familiar with what's called temperature sampling, where you're basically using this temperature parameter to then determine how equal the probabilities for the different tokens are. High temperature means the probability of all tokens is more similar, and then just sampling, or aka randomly picking one of the tokens. That's the type of thing that you're used to. But greedy decoding, which would be the most simple way of doing it, would just be to pick the one with the highest probability. And in this paper, they kind of realized that if you actually look at the top K, and it's not even like the top 10,000, we're talking about like the top 10. So in their examples, they really only say, okay, look at the top 10 possible tokens this could be, and explore down those little paths, right? They themselves use the word search, right? Search through those paths of possible tokens. And if you do that, you will realize that the paths that are the longest actually end up having higher prediction or higher confidence answers. So by the time you get to this token here and you're predicting this token 8, right, which is the answer to this question, the probability associated with this 8 token is higher than the probability associated with this 5 token. So this language model was right the whole time. The right answer was sitting in that language model. You just had to elicit it out of it. And right now, we're just using all these prompt engineering tricks to basically get the LLM to go down the right path, which is usually the path with the longest thread of chain of thought, right? The most amount of internal chain of thought. But if you could just search through all the possible paths, you probably find the right answer in there. And that kind of dovetails nicely with this paper here, where they found a similar kind of result where they say, okay, you can actually get better answers just by using an ensemble of LLMs. So rather than just asking one LLM the question, ask a bunch of different LLMs the question, or a bunch of the same LLM the question, get a bunch of answers, use some kind of similarity metric to figure out what the common answer is, and then use that one, and you can basically get the performance of a better model using worse models, just more of them. And the one sentence in here, which is kind of a throwaway sentence, but I think it's the best sentence in this paper, is that you could do this with a heterogeneous ensemble, which means that you could use multiple different LLMs from multiple different companies and providers and use their strengths together. And maybe that's kind of a future where we end up where you have multiple agents that are all kind of aggregating their answers together to give you your final answer. And then you can, in that way, then evaluate which agents you want on your team. So you have a team of agents and you're kind of building your squad, and you get to put different members from different companies in there. So I don't know, I kind of ranted at the end there. I feel like the summary wasn't as good as the stream itself, but hopefully you guys got something out of there. All right, so what do we got here? CFD is a prompting technique. Beam search is a sampling technique. Yeah, chain of thought decoding is... Chain of thought is this, right? So why is it called chain of thought? Because you have a chain of thoughts, right? So you see that it's not like there's no, like, chain just means like a bunch of things, a sequence of things. So here you have a chain of thoughts. The longer this chain of thought is, generally the better the answer is here. But sampling strategies such as the temperature or the beam search, it's like you're kind of looking through this, right? You're looking at the top candidates. Maybe you're limiting that. Usually the temperature sampling itself is usually not over the entire vocabulary. Even then, you're usually sampling over the top K, right? So even when you're doing here at a very high temperature, it's not like you're going to randomly pick this 3, because usually you're going to take all of these and then you're going to say, okay, I only want the top 4 though, but then within those top 4, randomly sample within those. Keeping everything in context is like a brute force of compute. Diffusion of thoughts is promising. That's kind of a cool idea. Diffusion models for language. We always get something out of these streams. I appreciate it. I appreciate the love, you know? But here's the way to think about it. You know, I feel like when I do a stream and it, you know, I like go back and I watch it and I cringe over the amount of times I swear, or the amount of times I use the word like, or the amount of times I like repeat things. You know, you could get mad about that, but the other way to kind of see it is that you could just thank the universe instead, right? So the way I kind of keep myself sane is that whenever I look at something I did in the past and I kind of cringe about it, I just think in my head, okay, well, thank you, universe, for showing me the things I need to improve, right? Because I can always become a better version of myself, but I can't become a better version of myself if I'm not even aware of my faults and the things where I'm incorrect. So yeah, whenever people, like some random person will comment and will be like, hey, you said something wrong here, like, you know, try not to get mad about it. Instead, be like, you know what? I appreciate that this person gave me feedback. I appreciate that I noticed something in my speaking patterns, and I'll try to make an actionable change to improve that going forward. So, I don't know, try to have this kind of like beginner mentality where it's like, it's okay if you're not doing things well. Just be self-aware and lean into the criticism, lean into the feedback, and see it as a good thing, right? Feedback is a good thing making mistakes is a good thing because that's how you actually get better. And that mentality is going to be even more and more important once you have AGIs, right? Because, I was talking about earlier in the stream how like people in the boomer generation don't know how to use keyboards, and we make fun of them for not being able to use keyboards, and the people in the generation under us don't know how to use, or won't know how to, or will use speech, and then we won't know how to use speech, right? So like every generation has certain advantages and certain disadvantages. And one advantage that we have kind of in the kind of like Gen Z, millennial, I don't know if there's Gen Xers who listen to my streams, but we have the advantage that we actually had to learn things, right? We actually had to like teach ourselves things. We actually had to do things and then fail and then try to do them again and then fail and then try to do them again. So we actually know how to learn. I think that it might not be a problem, but one of the problems that's going to happen is that once you have super intelligence, you're never going to have to do anything, right? The AI is just going to do everything itself, and you're never going to have like something you're never going to have this kind of like internal drive to improve yourself, because there's no point in improving yourself because the AI is always going to be better than you, right? So we're like kind of the last generation that learned how to improve themselves. So I don't know, use that as a gift, We'll probably be more intelligent than the generations under us, because the generations under us aren't going to bother to learn anything. Because what's the point of learning anything if you can just ask the AI to do it, right? And the same thing happened in pretty much everything, right? Like the generations before us, like the people 100 years ago, the people who were doing physics and math, they were probably way better at mental arithmetic than we are now, right? So what is the equivalent of that to right now, right? Like what are we good at that in 50 years, no one is going to be good at? And I don't know, just kind of lead to that. I think we'll learn from AI. Yeah, well, that's the thing. We'll go into that mentality. We'll be the type of people that we go into AI and we like, teach me how to do things, because we still have that kind of mentality that we want to improve as a person. Versus like the generations under us might be like, I don't need to learn anything. The AI is just going to do it for me. I have no desire to learn, right? So I think that desire to learn, maybe it's something that we learned from our specific upbringing and the way that we grew up with technology. Maybe as technology improves, people will have a different type of upbringing and they won't really cherish or think it's useful to like learn things and get better at things and try to improve yourself, because like who cares, right? The AI does everything. The AI will genetically engineer the learning into us as we gestate in our pods, basically. Okay, that's all I got, guys. We're a little bit over the 2-hour mark. Hopefully that was an entertaining and interesting stream. We're very close, guys. I think we already had AGI. Like, AGI has been here for a couple years, IMO, but we're very close to ASI. I think these self-play loops combined with agents, combined with things like this, we're going to have ASI by the end of the year, probably. So look forward to that, and I'll see you guys in the metaverse, and I'll look forward to slaying dragons with you guys in the metaverse. All right. Thanks, Amelie, Khalil, Spyro, Christopher, Majetti, Aries, Eleve, Jiha, Beyond. Who else? Aries, more Majetti, more Khalil, Justin, Christopher, the Yivian, Adam Levy, Ellie Katie, Beyond, Lit Guru. If I miss you, I'm sorry. Ed, Icky Phoenix, Work, Raphael, Nisio, 2ARX. Thanks, everybody. Hope that was entertaining. Tune in next week for more hot takes, and have a great weekend.